and or at least it was a practice test. Do you want me to start here, or do you want me to start with the problem? I really don't care. I could do the test. Here, good? All right. Um, Before we answer all the questions, do you realize that the pulley is applying a constant tension on the box? So if we consider the forces acting on the box from where it is right now, there's clearly going to be a tension force in this direction. There's going to be weight in this direction. And there's going to be a normal force that is slightly less than a weight in this direction. There's no friction in this section, so there wouldn't be any other force. These appear unbalanced to me. And since they appear unbalanced to me, I would suspect that the system is going to obey Newton's second law and will accelerate to the right. Just a brief thing that I want to remind you about, especially for your tests, that we have to assume second law unless it's been proven otherwise. But in this one, it's not an assumption. There's clearly unbalanced forces acting on the object, and since there's no friction, this system's going to accelerate to the right. So that first question, it says, consider all the forces acting on the block. What can be said about the forces acting on the block and their effect on the motion variables regarding the block? Be sure to explain how Newton's first and second law factor into the effect of the forces and the motion variables. Also, in your explanation, be sure to indicate if any of the motion variables are changing and how they are changing. That's a lot to have to answer. So keep in mind, if you don't answer everything that's there, you can't acquire all of the points that are available. Now, that was the biggest problem last year, is people only answered some of the questions and felt they were done. I'm seeing that there are several questions here. So let's start with the beginning. What can be said about the forces acting on the block and their effect on the motion variables regarding the block? All right, so that's a start. The effect is that the unbalanced forces are going to cause the block to accelerate, which makes this a Newton's second law problem. So I think that alone begins the answer here. Be sure to explain how Newton's first and second law factor into the effect on the forces and motion variables. Well, you could say that the second law is going to cause an acceleration. However, the first law acts in the y direction and the second law acts in the x direction. If you really wanted to explain yourself, you could also talk about the fact that the box is not accelerating up and down, but the box being on level ground will accelerate left to right. So it would make more sense to say it has a horizontal acceleration and not a vertical acceleration. Also, in your explanation, be sure to indicate if any of the motion variables are changing and how they are changing. Well, there are 5 motion variables. Assuming the initial velocity is 0, I think we can probably all agree that the box's velocity is increasing because the system is accelerating. Its displacement is probably increasing because as it goes faster, it is changing its position and it's changing it more and more as time goes on. Don't only talk about time as a changing motion variable. Time is always moving forwards. But the acceleration is decreasing. If you wanted all the points on this, you had to indicate that the acceleration was decreasing. And that's because this angle is changing. As the box moves, the cable pulls more upwards on the box and less to the side. So in this case, the acceleration isn't constant. Now, I wouldn't want a list like this. I would expect this to be kind of a paragraph form. And if we consider the number of points that were available here, I think the number one thing students will forget to do is talk about the fact that the acceleration is likely changing. That's only, bless you, that's only 1 point missing. That's not terrible. But if you didn't address all of these individually, well, then you're probably going to be in trouble. Now, would you like me to keep going? All right. When the block makes it to point A, the surface changes and the surface becomes rough. Also, a substantial amount of rope has been retracted by the pulley, yet the pulley still continues to pull with the same amount of tension in the rope. That's probably important. What possible... Go ahead and move that wherever you'd like. I'm going to put it back where I had it, though. the pulley still continues to pull the same amount of tension rope. What possible changes could occur to the motion variables due to the change in the surface? Be sure to explain how the frictional force is related to each change and consider that there are several possible outcomes related to the rough surface. That's right, there are several outcomes. The frictional force could be less than the horizontal force, so the box accelerates, but just not as fast. The frictional force could equal the horizontal force or be close to it, so the object could begin to move at a constant velocity for part of its motion. Or the frictional force could be greater than the horizontal force, and the box begins to slow down. Those are the three possibilities, and all three of them are possible. We have no idea which one may or may not be true. So you should have explained all three of those. Now, the middle one, where the net force is 0, that's terribly unlikely. Because the angle is changing, it would probably only be net force equals 0 for a moment as it passed through it, but it should be mentioned. Yep.
So the three possibilities were they could begin to slow down and then like constant acceleration, and then what was the third one?
There's no. It could continue to speed up, but just not as fast. Because suddenly we have tension, we still have normal force, we still have weight. All of these forces are still here, but now there's friction. So if the friction is little, it says rough, but doesn't tell us how rough. Well, if the friction was this big, then the system would still accelerate getting faster, but it wouldn't slow down. It just wouldn't be getting faster as fast as it was before. There could be the situation where the frictional force nearly matches the horizontal part of the tension. Basically, I'm looking at this part where this length here is about the same as this length here. In that case, the net force would be pretty close to 0 and it wouldn't be accelerating. There is the possibility that I've underestimated the normal force and the frictional force could be greater than the force to the right, the tension to the right. So now the friction being greater than the force to the right, the block would slow down. It'd still accelerate, but the acceleration would be negative. This would cause the velocity to become a smaller number. All three of those are possible. Question 3. Which property, the angle of the rope, the pulley force, or the stickiness of the surface would have the most impact on determining which outcome from above would occur, and explain? There is no right answer there. Meaning, as long as you justified your position, you would probably be okay. And just to understand, all better? I find this kind of funny now. But I'm going to put it back to where I had it, so if you don't mind. Right there's kind of where I want it. So yes, every time you guys touch the screen, you can change what's going on. And I can't lock you out. So that is one of the downsides. I could go into this, and I think I should. You could solve for this, meaning net force in the x direction would be T cosine theta minus friction, and that equals MA. It's perfectly acceptable for me to ask this question as a calculation. So you would put a free body diagram there, you would wrap a triangle around the tension, and you would be able to figure out what the net force is. And I don't think it's too much to ask you to do this. Net force in the y direction is going to be normal plus T sine theta minus mg, and that has to equal 0. Now, I'm unlikely to ask you to do all this because it's a lot of algebra. But the reason I'm doing this with you for a moment is for you to understand that there is part of this I expect you could be doing. So I solved this for normal force, and friction has to be mu times the normal force. So this is the thing to look at. Now, you don't have to do all of this to answer the question. But what I'm saying is, if you did do that, It's asking the stickiness of the surface. That's mu. It's asking about the angle of the rope and the pulley force. Which of these has the most to do? Stickiness of the surface. It has the most to do with what's going to happen because it affects everything there, right? It's multiplied out front. So that would have the biggest impact. But I think you can make a reasonable argument without doing this that the other forces contribute. Probably the least impactive would be the tension. The most impactive would be the angle outside of the stickiness. But as long as you picked one of them and talked about it successfully, you would be fine. So here's what I would say. If you said tension, having a lot of tension, regardless of how sticky the surface is, would probably mean that the system would accelerate to the right regardless. Increasing the angle a lot, well, that could lift the block off the surface. What does that do to friction? Well, it makes friction go away completely because it's no longer touching the surface. But the stickiness is what ramps up the size of the frictional force. So as long as you picked one of those and discussed its connection to the net force, you were fine. And if you picked more than one and indicated how a change in that one was connected to the net force, you were fine. I believe last year I gave 3 points for this total, which is generous. It probably would only be 2 on the actual AP exam. Keep going, or am I good? Or I'm sorry. Am I good to go on, or do you want me to say more? Right. If it isn't apparent, while the rope has been retracted by the pulley, although the tension of the rope hasn't changed, the proximity of the block to the pulley has caused a change in the angle. What forces have been impacted by this change, and how would the acceleration of the block at points past B be different than the acceleration of the block at point A? Past B is important because it's indicating that it's no longer on the rough surface, so we don't talk about friction. What would be impacted as the angle got bigger? Well, as the angle gets bigger, the amount of force to the right gets smaller, and the amount of force upwards gets larger. So the two forces that are impacted is the horizontal component of the tension and the normal force. The normal force gets smaller as you pull up more on the block. But the horizontal part of the tension, it also gets smaller, which means the rope's going to be less effective at pulling the block to the right because it's pulling more up on the block. Part B just has you do the same thing with friction. So if the normal force gets smaller, the frictional force gets smaller. It's really all you have to say. The only additional thing that happens when it's on in that section from A to B is your indication that as you pull more up on the block, you reduce the normal force, therefore you reduce the frictional force. You say that, you're good. All right. An expository question like this on the actual AP exam is very likely to be about 7 points. I think last year I gave this one like 12 or 13 points. There's a lot to talk about. The only difference between this year's test and this test, I think this is last year's, is I didn't ask a question like 3 where any one of them could be the right answer. I've only asked questions where there is a single correct answer. I found when faced with something like that, students spend too much time trying to decide. You have a finite amount of time. All right, so go on to the next page. Or is there anything more about this one you'd like me to talk about? All right, so this one, definitely what could be on your exam. There's nothing wrong with this one. The only thing I would probably say is I kind of believe this might be a little bit beneath what we can do. I think we can probably do more than this, but in looking at how to do it, question one was to show all the forces acting in the box while it's traveling. You should have had only 3 forces drawn there. So I was expecting you to have weight, of course. All right, so there. So weight. There's a pushing force downwards too, and it's at some angle. And then the ground has to respond by applying a normal force. And I think my 2 forces down have to be able to equal the 1 force up. So I don't know what you want to call this, push, whatever. It says that the force is applied at an angle of 30 degrees. So this is 30 degrees. That makes this 30 degrees. And some of you are going to screw up the angle tomorrow. Sorry. Good luck. Figure out your angle stuff. But that's where the 30 degrees should go. So question 1. The downward force is constant. What is the size of the normal force acting on the box? Should I continue or not? You guys want to know? All right. Horizontal force is going to be whatever that is, 50 cosine 30. And then the vertical force, 50 sine 30. We good there? Do I need to explain that? Am I good? All right. Net force in the y direction is 0. The box is not accelerating up or down. So I have 1 force up, 2 forces down. And that has something to be equal to 0. The box is 15 kilograms. So that's normal minus 15 times 10 minus 50 times 0.5 equals 0. 150 plus 25, so normal has to equal 175 newtons. Good. Describe the motion of the box during the time that the box is receiving the 50 Newton force. If it is accelerating, please find the magnitude and direction of the acceleration. It is accelerating. The forces are unbalanced. So net force has to equal MA. There is only one horizontal force, and that is the component of that pushing force to the side. So that's going to be 50 cosine 30 degrees equals MA. To find the acceleration, that will be 50 cosine 30 degrees equals 15 times A. So I'm not even sure. I'm probably about 3 meters per second squared. I'd probably provide a better answer than that, but 3 is close.
2.9.
All right. Question number 4. The area where friction is negligible is approximately 10 meters in length. Calculate any relevant motion variable that could be used to describe the box's motion while receiving this force. That's delta x, v initial, 0, v final, unknown, acceleration, known, and time. So this is going to be 10 meters. You have a motion problem now. Kinematics, know your motion equations. Figure those out. Tomorrow you get the equation sheet that goes with the exam. It has several motion equations on it. So I could work this out. Do you want me to? So v final squared minus v initial squared equals 2a delta x. So that'll be v final squared minus 0 equals 2 times 3 times 10. So v is the square root of 60. That's v final. So that's how you get one of the answers. To get the time, I'd probably use delta x equals 1/2 a t squared plus vi times t. So that's 10 equals 1/2 times 3 t squared plus 0 t. And then, let's see, 20 divided by 3, so square root of 20/3. Those would be your 2 answers. Make sure you put the units down, meters per second and seconds. Good, move on. Next question is probably where I'd put a little more weight. Eventually, the box encounters an area where the surface is rough. This generates a frictional force that is 40% the size of the normal force. What is the size of the frictional force? That's just friction equals mu times the normal force. So you really don't have to do very much. We already calculated the normal force several steps above this. So this is 0.4, 40%, times the normal force of 175 newtons. That is the size of the frictional force. 70? How does this affect the acceleration of the block? There's only one way to know, and that's to recognize that the net force in the x direction has now changed. The net force in the x direction is now going to be, let's see, 50 cosine 30 degrees minus friction, which has to equal ma, and friction is 70. So 50 cosine 30 minus 70 equals 15 times a. And this is going to be negative because 50 cosine 30 has got to be less than 70. So it's going to slow the box down. I think this came out to be like negative 2. But it's going to slow the box down. How does it affect the acceleration of the box? I think you should be making a comparison here. You know what the original acceleration was? You should be making a comparison. The box is now slowing down. The acceleration became negative. It's in the opposite direction. The box is not speeding up anymore. All right. That's a practice test. 10 minutes each question. So it's 20 minutes maybe. You might take a little bit longer. I don't think this, as a problem goes, was particularly hard. I think we could do more challenging things, but I don't think it was terrible either. I'm not sure all of you found it to be easy. By the look of how feverishly some of you are writing, either you didn't do it yesterday or you never looked at the answers I posted or something else. I'm not sure which. But it was supposed to be something you did yesterday. You had 42 minutes to try. All right. Is there anything else I can talk to you about? We still have about 15 minutes. Yes, sir. I can make every. So number 33. You want to use a rope to pull a 10-kilogram box of books up a plane inclined 30 degrees above the horizon. The coefficient of kinetic friction is 0.3. What force do you need to exert on the other end of the rope if you want to pull the box at a constant speed, or if I want to pull the box with acceleration of 0.5 meters per second squared up the plane? All right. There's every reason to believe I could put a question like this on the test. So I think we can assume that the rope is being pulled in the direction of the plane. That seemed pretty reasonable to all of you. And if I consider the free body diagram on the box, then I think we have a total of 4 forces acting on the box. I'm just going to draw the free body diagram right on the center of the box. So weight, tension, normal force, and a frictional force. Any question on where any of those forces came from? I've just gone through my list of forces. I didn't do it particularly out loud, but I think that we've talked about this a lot. I'm going to impose a coordinate system, and I'm going to choose one that is aligned with the ramp for two reasons. One, it aligns with the most number of forces, but also we know that in a later portion of the problem, the box accelerates up the ramp. So I need to make sure my positive x direction is in the direction of the acceleration. So I'm going to make this the positive x direction, and this is the positive y direction. That makes this the negative direction, and this the negative direction. I'm going to recognize that because it's on a ramp, the angle goes here. There's the angle between the weight and the force that lines up with the y-axis. My last step here before I start dealing with Newton's first and second law is to break up my weight into its components. And I'm going to assume that you guys realize there's a component down and a component to the left. This one will be mg cosine 30, and this one is mg sine 30. Any question about any of those decisions? Okay. The net force in the x direction equals 0 for part A, because it says that the box travels at a constant velocity. The net force in the y direction has always been 0. So let's break our forces down. In the x direction, I have tension minus friction minus mg sine 30 equals 0. Any question about where any of that came from? All right. Normal minus mg cosine 30 equals 0. Any question where any of those came from? All right. So normal equals mg cosine 30. They gave me the mass of the box. It's 10 kilograms. We know g, so I think we can go 10 times 10 times the cosine of 30 degrees. And cosine of 30 is 0.866, so 100 times 0.866 will be 86.6 newtons. This is the size of the normal force. Again, this is the only thing I mean, this is what the information leads me to do. I don't know if I need that information. I'm just following the set of steps as given to you guys. We're asked to find the tension, and it looks like the only way I can find tension is if I know the size of the frictional force. Bless you. Friction is equal to mu times the normal force. They told me mu, 0.3. So 0.3 times 86.6. This is going to be the size of the frictional force. Can somebody bang that out on the calculator for me? Just throw that anywhere. It's okay.
25.98.
I'm going to put 26, but you guys should use 25.98. So we're supposed to find the tension. So I am now going back to here and saying tension equals 100 times 0.5 minus 26. Yep.
You mean plus 26?
Plus 26. So that's 76. But you'll probably have a decimal value because you will not have rounded as much as I did. This is not the answer in the back of the book. The answer in the back of the book is a slight difference because the back of the book uses 9.8. So if you want the answer in the back of the book, redo the problem with 9.8 and you'll get their answer. It's close. Can I answer any questions about any of the choices I made here? You guys okay over there? All right. The problem is changed in part B. It says I have a constant acceleration of 0.5. So that doesn't change very much of what's here. It does suggest, though, that the net force in the x direction is not 0. The net force in the x direction is going to now be ma. I'm not redoing the problem because it's the only thing that has changed. ma is now here. The mass was 10, so this is 10 times 0.5. So when I added all those things to the right side of the equation, I still have to add in my 10 times 0.5, or 5. So my actual answer will just be 5 newtons more. So I pull with more tension, it increases the acceleration. So, yeah. Testable tomorrow? I see no reason why not. The only thing that I don't like about this is that you guys tend to have difficulty rotating the axis, and you tend to screw up these two components. I don't know why, but having done this for years, I can probably speculate it's because this test lines up when most pre-calc kids are first starting to do the unit circle, and they just are they're just rattled. But you can memorize the two components. They will always be the same if you have just a standard incline problem, and this is a standard incline problem. Yep.
What would a non-standard incline problem look like?
There are reasons why you may not want to rotate your axis. There are situations where that occurs. In those situations, this is going to be the same. Will we see them? Maybe we'll see. I don't know that I have to hurry out and try and find things that don't conform to what we've been doing. So you won't see it on a test tomorrow, if that's what you mean. Yes, ma'am. Tomorrow there will be two FRQ style questions. One of them is going to be, could be this. This is no problem. Could be like we just did on the practice test. To me, that's no problem. I will say there are two different versions of the FRQ, and they have drastically different situations, but same number of forces. They both are going to concern the idea of the coefficient of friction. They both are going to concern having a force that is off axis that you'll have to resolve into components. So everybody will have the same skill set that's being tested. There will be a qualitative question, which is going to present a situation and have you provide some kind of expository answer, your written paragraphs of stuff. I think that it would not be too crazy to think that I would probably ask questions about static friction there. It seems like one of those things that's a nice, tricky topic. Let's see if you've got an idea about that. And I can see that being a good place for that. But it not dissimilar to what you saw there with the pulley and the changing angle and stuff like that. Something purposely, something that I would purposely make that would make you have to think about what's changing and how it would affect the answers. Does that make sense? In this case, I was changing the angle, purposely seeing if you knew that change changed the normal force and therefore changed the frictional force. So I can totally see something in a very similar vein. There will be a group of multiple choice questions. So multiple choice questions to me are the kind of plug and chug stuff you'll see that we've talked a little bit about, but it's also going to be questions where I'm going to try to intentionally trick you. Things like, you throw a ball in the air. When it comes to rest at its maximum height, what's the acceleration to see if you'll put the 0? Well, there's a few things about forces like that we talked about too. I'm probably likely to do something like that on your test. 10 multiple choice questions, a expository answer, and a problem answer. I think that should take up to 45 minutes. And yeah, you should expect there to be multiple versions of the test tomorrow. I would encourage you to have a ruler tomorrow. I will have a box on the test in 2 different places where you'll have to draw a free body diagram, and you will not be able to use that free body diagram to do your work, because I'm going to say don't put an axis on here because we're going to grade that separate. And then yeah, that's it. I think it's the test is all it's like 3 pages, but I think I'm printing out 4-5 pages for you, because you'll also get your equation sheet tomorrow as part of your test, which you will rip off and keep with you. So, all right.